All right, we're going to finish this chapter with logarithmic and exponential equations. Now, earlier we talked about a couple of properties of the one-to-one property of logarithmic and exponential equations. Remember, logarithms are exponentials, just written in a different form. So both of what I have here are consequences of one-to-one properties of logs and exponential equation. The one on the left says if you have a logarithmic or an exponential equation, because you have equal sign, if the bases of exponents are the same, you simply equate the exponents, the powers. The one on the right, kind of similar. If you have log x equal log y, with the same base, valid base, go a in this case, then the argument of the logs will be the same. Okay, so let's actually see how we're going to solve some equations. Now, the both types, logs and exponential equation we solve, are pretty much in two broad categories. So let me tell you what I mean. The first category, first type of exponential equations are like this, where I have an exponential expression on the left and a number on the right. Now, the first type is the kind that where you can rewrite the number on the right side with a common base as 2 cubed, common base as the exponential on the left. Now, when that happens, that's precisely what the property above is. Bases are the same, the exponents must be the same, therefore we are done with this one. We were able to solve it. So that's the first type of exponential equations. Now there are other types where we cannot get a common base. Okay, so for example, let's say this other type, suppose instead of 2 to the x equal 8, I have 2 to the x equal 5. See, now I cannot write as 2 to what whole power. See, I can't do that. So for these types of exponential equation, we simply rewrite them in logarithmic form. Okay, and the rewrite of in logarithmic form was the following. If you recall, when we had x equals a to the y, we said this can be written as log base a of x equals y, right? So using this property of logarithms, I can rewrite my exponential equation. So that means log base 2, the 2 base of the exponent is base of the log. The exponent x goes on the other side by itself, and the 5 moves to argument of the log. And there you have it. Notice how easily I was able to solve this. This would be the exact solution, we call it. The solution is log 5 base 2. Now, if I want to approximate this, I want to, let's say, get a number out of this, I can always use my calculator. Using change of base, I can go ln of 5 over ln of 2 equals to some kind of a number here, right? Round it to 2, 3, 4, whatever decimals we need to. So that would be the second type of exponential equations. Okay? So let's take a look at another exponential equation. This one's slightly more elaborate. I'm going to look at the second type where there is no common base. There we go. Because the ones with common base are fairly straightforward and easy to do. Now, what if they look like this? Well, for something like this, another way now to do this is because I have now two exponential functions, right? One on either side. So I couldn't do what I did with my early example, 2 to the x equal 5. Okay, so for these types, I guess that makes it 3 types of exponential equation. For these types, what we do is this. We're going to take natural log ln of both sides. We can do anything, just about anything with equations. That's the other thing. You can raise equations to the same power. You can take roots of both sides. You can take logs of both sides. I'm choosing to go with natural log because it looks nicer and cleaner. So when I do, here's what the left side is, right? And what is the right side is ln of 3 to the x minus 1. Well, using properties of logs, this one, ln of a to the r, is going to be r ln of a. Okay, or in general, log base a of m to the r is r log m base a. Either way, I can use this property to rewrite the left side. The left side is now x times ln of 2. And remember, ln of 2, I can use my calculator, is a number. It's just a constant, just like 2, 3, 4, 5 are. It's just a fancy number. ln of 3 to the x minus 1, I can bring x minus 1, the binomial, in front of natural log of 3. Again, another constant. Okay. Now, let's distribute. So I have x ln of 2. And the reason I write it as that is you can actually do this, ln of 2 times x there. So this is, again, no different than 5x and numbered a coefficient times x. That's what that is. Okay, let me write it like that. Distribute the constant ln of 3 to x and -1. And bring ln of 3 times x to the left side becomes negative ln of 3 times x. And keep it on the right side. Keep it on the right side as negative ln of 3. That's the distribution, correct? Now, what do we do next? Well, I can factor the x out, correct? On the left side. So I have ln of 2 minus ln of 3 equal negative ln of 3. Okay, so we have that. And what are we going to do next? Or next, let's divide both sides by the coefficient on x. So I have negative ln of 3 divided by ln of 2 minus ln of 3. You can move the negative in the denominator and distribute it to the binomial. And here's why. Let's say I have -1/2 like that. See, the negative in a fraction is very dynamic. You can move to the top, to the bottom, or in front of the fraction line, right? All of these are -1/2, -1/2. So I'm choosing to bring negative in front of the denominator. Okay, and when I do, what am I going to get? I'm going to get ln of 3 divided by ln of 3 minus ln of 2 once I distribute the negative to the binomial. And then the denominator, I can write it as quotient. Remember, difference of log is log of a quotient. That's ln of 3/2. All right, and we can combine this or just leave it the way it is. There you go. That will be the solution. It's going to be ln of 3 over ln of 3/2. All right, or we can combine it as, and this is for the die-hard, you can put it as log 3 base 3/2. This is also permissible. Alrighty, so we're done with this example. Let's take a look at another example. Okay, let's take a look at our next example. Let's do an example with logarithmic equations now. So suppose I have log base e of x equals 4. Remember, that means natural log of x, right? So I can rewrite this as x equals e to the 4th. And there is a solution to this one. See how easy it is to solve them once we redefine them in exponential form. Again, what I had was ln of x equal 4, but I rewrote it as log base e. So that is a solution to ln of x equal 4. The answer is e to the 4th power. So that's one type of logarithmic equation where you have a single log and a number on the other side. You just rewrite it. What if I have logs on either side? Log x squared minus 1 equals log x plus 1. Let's go in base 3 in here. Now, going back to the first property we had, I can use the property of logarithms and just simply equate the arguments. So in a way, it is as if we cancel the logs. Now remember that canceling, quote unquote, canceling of the logs, you can only do it when you have a single log and a single log here. If on one side you have two logs, you cannot cancel these logs. Okay. And we'll see example in a moment of that. So here I have x squared minus 1 equal x plus 1. I see a quadratic. So bring x to the left side, subtract 1 from both sides, get 0 on the right side when you do those. Okay, and the factored form of this would be x minus 2 and x plus 1 equals 0. Right, and then what I need to do is by zero factor property, x is 2 or x is negative 1. Now one thing here, by the way, very important. When we solve the exponential equation, x3 and here x whatever, log 5 base 2, and down here, this was the solution. I don't check these solutions if I'm comfortable with the way that I found them. But when it comes to logarithmic equations, because of all the manipulations that we do throughout, we need to check the solution to every logarithmic equation. Okay? And what we're checking is whether we are in the domain of a log or not. If you recall, the domain of all logarithms, if you look at the graph, for example, this was graph of log base a of x. Suppose a is positive, so it looks like this. The domain of logarithmic function is x has to be positive, regardless of whatever the base is, the valid base is. Base could be greater than 1 or between 0 and 1. In either case, the domain has to be positive because we cannot process 0 or negative values for the log. Okay, so because of that restriction, I do need to check the solution, and here's how I check. Let's go back to this one, the first one I did. You just plug in e to the 4, the solution, you plug it in for the argument of the log. If the argument is positive, I'm done. So I don't have to actually show two things equal to each other. Okay, but in this case, if I did check it, here's how a full check would look like. I'm going to put e to the 4th, which is the solution, in for x. Now, using properties of log, that's 4 log EE. Log EE is 1 because base and argument are the same. Using properties of logs, that's 1. And there you go. We just showed that the left side is equal to the right side. So that is a full verification step to show left and right are exactly identical. What I checked for again was that e to the 4th, is that positive? Yes, e to the 4th is positive. Whatever that number is, remember e is approximately 2.718, right? Raise that to the 4th power and you get a number. If you think of 3 to the 4th is 81. So this number is going to be less than 80. But whatever it is, it's going to be positive. So that's what I'm checking for. Now let's check these numbers I have here into my logs. So I'm going to check a 2. 2 squared 4 minus 1 3 is positive. Yes, it works. Plug in 2 in here. 2 plus 1 3 is positive. Yes, so we're going to buy that 2. The answer is 2. This is good. Let's try negative 1. I'm going to plug in negative 1 here. Negative 1 plus 1 is 0. Is 0 greater than 0? No. And remember, argument of the log cannot be 0 or negative numbers. Therefore, it doesn't work in this one, although it works in here, let's say, which it won't. Even if it worked in one, that's not good enough. It's got to work in both, so because we need to get an answer from each log. So I'm going to discard this. The final solution is just 2. There you go. That's the only acceptable solution. All right. And so there, we've solved that one. Let's take a look at another example. In this example, suppose I have 1/2 log x in base 7. So that's going to be 3 log 2 in base 7. Okay, let's say that's the left, that's the right side. And I want to solve this one. So on the left, see I have log on either side. The thing that we don't need are these coefficients. So I'm going to move them to the exponent. That's going to be x to a half, and on the right side it's going to be log base 7 of 2 cubed. Now bases are the same you can think of in terms of canceling the logs, right? And from this I get x to 1/2 is equal to 2 cubed, which is 8, right? 8. Now how do I solve this equation? We're going to square both sides. X to a half squared, that's just x, and 8 squared is 64. And there we have. So the solution is 64. And remember, we got to check. The check will be easy here. Plug in 64 for x. Is the argument positive? Yes. We're done with the check. See how easy it is, but you definitely want to check these. Okay, don't forget that. All logarithmic equations, the answers must be checked. Let's do another example. Suppose I have common log of x plus common log of x plus 15 equal to 2. Again, this is the kind that's going to have log on one side. It's kind of like the one I started with, right? Log base e of x equal 4. So I need to combine the two logs on the left into log of a single expression. Sum of two logs, same as log of a product. So I can write it as x times x plus 15, set it equal to 2. And again, this is a common log, right? Because the base is 10. Let me put that 10 so you know it's there. But again, we don't write it typically. All right. And the next step is to rewrite this using exponents. So the left side is going to be distribute x squared plus 15x, and the right side 10 squared, which is 100. Actually showing that missing base of 10 helps me rewrite it in the exponential form. And then I can see, oh, I dropped my 15x. I know all of you caught that. I didn't. There he goes. X times 15 is 15x. So here's 15x minus 100 equals 0. And this is factorable. We can write it as two numbers that multiply to negative 100. That will be negative 5 and 20. The sum is 15, which is the middle term. Perfect. That's going to work out. So at this point, we get two potential solutions, negative 20 and 5. Now, just because you get a negative x, you do not rule it out. You do not rule it out. The only time you rule out is when you plug it in and it doesn't work. Sometimes you plug in positive numbers, potential positive numbers, and they don't work. So let's try the 5 here. 5 plus 15, 20, positive. Yes, that works. 5 in here, log 5 is positive. Yes, it works. So we'll keep that. 5 is a good solution so far. Let's try negative 20. Negative 20 in here, log of negative 20. Oops. That's not positive, so we're going to throw away. We threw away and it happened to be a negative number. But again, I want to emphasize, just because you get a negative number, don't naturally just cross it. Oh, that's negative, so it's not going to work. You have to check it. Check. And if it doesn't work, that's when you get rid of it. And I emphasize, sometimes positive numbers do not check. So just because you have positive, negative, that's not the deciding factor. The check is. Okay, let's take a look at this example now. I have 2 times log x minus 3, and let's go base 5 minus log 8 in base 5. And this time I'm going to throw in a log on the right side, see? So I have log on either side. And here's what I cannot do. There you go. That would be incorrect. You cannot do that. We don't have that property of logs. The only way this property works is when you have a single log on the left, single log on the right side, not combination of logarithms. Okay. Therefore, to that extent, I'm going to rewrite the left side. I'm going to move 2 as an exponent on the argument of the first log. So it's going to be log of x minus 3 squared negative log base 5 of 8. And then we're going to put these together as a quotient, right? Difference of logs, log of a quotient. So it's going to be x minus 3 squared divided by 8 in base 5. And that's going to equal to the right side, log base 2 of 5. That's this one. So I just copy that. Okay. Now we have single logs on the left, single log on the right. We can now cancel them, or think of canceling them. The one-to-one property says arguments must be the same. Therefore, x minus 3 squared divided by 8 is going to equal to 2. And we can multiply both sides by 8, and I get x minus 3 squared equals to 16. And then use the square root property of equations. Let's take the square root of both sides, and that'll be x minus 3 equals, when we take the square root using the square root property, the moment you do it, you have plus or minus on the right side, on the constant. So this is going to be plus minus 4. Therefore, x minus 3 equal plus minus 4. Now the way we handle this, if I add 3 to both sides, I get 3 plus minus 4. So that means once you add 4 to get 7, the other you subtract 4 to get negative 1. And we have two, again, what I call potential solutions at this point. The solutions potentially are 7 and negative 1, right? They become solutions once we check them in the original. And always check in the original. Don't look at this one in between, the one that's manipulated. So let's go with 7 in here. 7 minus 3, that's 4. 4 is positive, yes. And that's the only place where you have a variable logarithm. The others are just constant. Good, so we'll buy 7. Let's try negative 1. Negative 1 in for x, negative 1 minus 3, negative 4, is that positive? Nope. So again, here's a case where the negative number did not work. But I want to emphasize, just because it's negative number, don't toss it out. Definitely check it. Definitely check it and make sure it works or doesn't work. Okay, so we have another example done. Let's take a look at more examples with these. Again, the more the better. 2 to the x equal 10. Again, for this one, we can rewrite them, right, using definition of logarithms. You can go log base 2 of 10 equal x, and that solves it, right? Now, because that I see a 10 here, let's use a change of base. I'm going to write log 10 as common log of 10 and log 2 as common log of 2. And the reason is because log 10 base 10 is 1. That was the property we did in the previous lecture, right? One of the properties of a log was if the base of the log argument of the log are the same, the result is 1. So this is going to be 1. Therefore, the answer to x is 1 over common log of 2. I could have done natural log, but the answer wouldn't come out as nice. Then I have ln of 10 over ln of 2. So right now I have simply 1 over common log of 2. All right. Let's take a look at another example here. Suppose I have 3 to 1 minus 2x is equal to 4 to the x. Again, when you have exponential functions on both sides, on either side of equal sign, we just take natural log of both sides. That's ln of 3 or common log, either way would work. And I like natural log because that's usually what you do in your calculus courses. We use natural logs. They work out nicer, a little bit nicer. And there we go. I'm using the properties of logs, bring the exponent as a factor in front of a log. Then distribute ln of 3. Remember, ln of 3 is just a number. Distribute it to the binomial. What do I get? I get ln of 3 minus ln of 3 times 2 times x. And on the other side, we just have x ln of 4, right? Now, let's see. I'm going to keep ln of 3. and 2 times ln of 3. In this expression, I'm going to move it to the other side. And it's going to be 2 times natural log of 3 times x, positive on the other side, plus natural log of 4 times x. Okay, and now I can factor, sorry, what did I do here? It's ln of 4 times x, this one. I just move ln of 4 in front. Okay, now I can factor an x here. Factor the x, so what do I have? I have 2 ln of 3. Well, 2 ln of 3, isn't that ln of 3 squared when you move 2 to the exponent of 3? And 3 squared is 9, so that's ln of 9. Okay, therefore I can write this as natural log of 9 plus natural log of 4. On the left I have ln of 3. What else can I do here? Well, ln of 4 and 9, sum of the log of a product. That's going to be ln of 9 times 4, 36. Right? And to the left, I have ln of 3. From here, divide both sides by ln of 36. So I have ln of 3 over ln of 36. So this would be one answer that's permissible, or again, we can combine it as using change of base as log 3 over log, log 3 in base 36. This is using the change of base. All right. And there we have it. So many ways we can write these. And also, by the way, let's say here where I have right in here, from that I can also do the following. I don't have to go to ln of 3, ln of 9, right? I can keep them the way they are. So in other words, this is what I'm thinking. There's so much flexibility in the answer here, it's crazy. So we have ln of 4 plus 2 ln of 3, right? There's your 2 ln of 3, there's ln of 4, and I combine them. All right, and once we have that, now divide both sides by the binomial. Here's one possible solution. It really depends on how you want the solution, but all of these are acceptable. Notice this is good, and this is good. 3 different ways to report the answer. Now, ln of 3 over 2 ln of 3, or right in here, that's going to be a positive number, right? Ln of 3 divided by ln of 36 is going to be positive. And because we have exponential equations, we don't need to check. And the reason is because domain of exponential equation is all real numbers. See, anything, as long as we get an answer, the answer is going to work. So it's only with the logs that we have to check. All right, let's take a look at another kind of exponential equation that would be like this. All right, now this one is slightly different. And the way to work this one is the following. The 3 to the 2x, I'm going to write it as 3 to the x quantity squared plus 3 to the x minus 2. Now, 2 ways we can do this. We can just factor it the way it is, or we can let, say, m represent a second variable, represent the exponential portion of that equation. If we do that, then 3 to the x squared is simply m squared, and 3 to the x is m. And there you go. We get what we call an equation that is quadratic in form. The original is quadratic in form. What we mean by quadratic in form is exactly what you're seeing in this box. That means we can rewrite, or we can rethink that equation as underlying a quadratic equation. Okay, and there you go. And then we can factor this quadratic equation now. M plus 2, m minus 1, and solve for m, right? So m would be negative 2 and m is 1. Now that's not the solution to the equation, because the variable is x, not m. So I need to go back in here, and plug in for m. Okay, I'm going to plug in a 1. So 1, that's what m is, equal 3 to the x. And 3 to the x equal 1, rewrite it in logarithmic form. That's going to be log 1 base 3 equal x. Log 1 in any valid base is 0. So x is 0. You see that? And another time, m is negative 2. So I'm going to go negative 2 equals 3 to the x, and the same work. That means log base 3 of negative 2 equal x. And what do you think? Argument of a log isn't allowed to be negative or 0. So this one has no solution. Therefore, negative 2 is ruled out. And the only acceptable solution is x 0. See how that works? X is 0. There is our solution. Now that's one way we could have done it, or we could have, from get-go, we could have factored this right off the bat. 3 to the x times 3 to the x, that's 3 to 2x, right? Remember, 3 to the x times 3 to the x. Using properties of exponents, you add exponents, so you get 3 to 2x. You don't multiply x and x, get x squared. All right, so that's 3 to the x, 3 to the x. The number is going to be plus 2 minus 1. I'm thinking FOIL, first, outer, inner, last. When you do FOIL, you're going to get exactly what's up here. And set it equal to 0 and solve each of those. 3 to the x plus 2 is 0, or 3 to the x minus 1 is 0. From this, 3 to the x is 1. From the first one, 3 to the x is negative 2. But then both of these equations, you see that? We see them here, and we see this one here. We've already solved those. These are your next steps. Okay. So you get the same outcome. The difference is I was able to factor it here right off the bat. And some people like this other alternative where you create what we call an auxiliary variable or a secondary variable and then work this through. So however you do it, that is the solution. Okay, and we're done with that one. Let's take a look at one last example here. Okay, in this example, suppose I have natural log of e to the x plus 3 is equal to, or actually, let's not make it so easy. Let's say I have e to the x plus 3 is equal to pi to the x. Notice I have two exponents, exponential functions on either side because they each have a power of variable x. And the bases are not the same. So when that's the case, we usually take natural log of both sides. So from this, I'm going to use color. So I'm taking ln and I'm taking ln of the right side. That's what I'm doing. So it's going to be ln of e to the x plus 3 equals ln of pi to the x. You see that? It's called taking log of both sides. Now, ln of e to the x plus 3, that's just x plus 3. The exponent moves in front of a log, right? And times ln of e to the right, x moves in front of a log, ln of pi. Ln of e is 1, because that is log base e of e, which is 1. So to the left, I have x plus 3. No need for parentheses now. And to the right, I have a constant, ln of pi times x. So what do? I can bring ln of pi times x to the left becomes negative ln of pi times x. And move 3 to the right side, and the right side becomes negative 3. Then factor the x. Or at this point, you can multiply. What if I do this? Let's say I multiply both sides by negative. So the left side becomes ln of pi x minus x equals 3. There, multiply by negative 1. And then factor the x. When I factor the x, I get ln of pi minus 1 equals 3. And then divide both sides by the coefficient on x, and 3 divided by ln of pi minus 1. And there is the solution to this one. Because it's an exponential equation, the domain of those are all real numbers, so I'm sure this solution is going to work. Okay. And there we have that one. So we are done with this lecture again, and hopefully you followed everything we've done. And that wraps up this section, logarithmic and exponential equations. Again, thank you for watching.